So, hello everyone. Thank you for attending another StarRocks webinar. My name is Cedar Shen. I am a StarRocks contributor, and I'm also a product manager at Data. Ron is joining us. So, Ron, do you want to introduce yourself a little bit?
Yeah, thanks for the introduction, Sita. My name is Ron. I'm also a StarRocks contributor, and I am a developer advocate here at StarRocks. Excited to be here.
Okay, so today's topic is on 4.0. We just released 4.0 on the 17th, a few days ago. No delays this time. Congratulations, team. Right, so today we're gonna first let's go over the agenda first, right? So first, 4.0 is released, right? And first we're gonna give a high-level overview of StarRocks for the folks that are not familiar with StarRocks, what kind of use case and architecture, StarRocks supports. And then we're gonna dive deep into the 4.0 features. First, we're gonna talk about performance. We achieved around 60% year-over-year performance gain, and also on other type of workloads such as JSON performance, right? Always trying to achieve the best performance, the best cost efficiency for all of the StarRocks users. And then we're going to talk about data lake analytics, talk about our deepened Apache Iceberg integration. And then we're going to talk about authentication, authorization, access control, data governance, right? And then we're going to go into the storage side of things, our features that we built, to reduce the cost for real-time analytics running on S3, right? And other type of quality of life improvements and even more type of workloads that StarRocks 4.0 supports now. And then we're going to talk about 4.x, beyond 4.0, the roadmap and what where the project is heading and what we're going to do in the near and long term in the future roadmap. Okay, so let's get started. So first, let's go over StarRocks. StarRocks is a Linux Foundation open source project focused on low OLAP-like use cases, on analytical use cases, right? So first, you can deploy StarRocks as a data warehouse, right? It has its own storage engine that really supports those like real-time use cases, right? Sub-second queries at scale, right? So we have the best in-class performance. We can run on-the-fly joins with no denormalization. And most importantly, with our own storage engine, you are able to achieve real-time mutable data directly on your columnar storage with around like 10-second data freshness, right? So mutable data on your columnar storage, 10-second data freshness, right? With StarRocks' own storage engine. And also it features a storage and compute separator architecture. So basically what it means is that you persist your data in S3 and your local nodes, your EC2 instances are used as execution nodes only and caching, right? So this is deploy StarRocks as a real-time data warehouse for your real-time like workloads. And then you can ditch, the StarRocks storage engine and use open table format, such as Apache Iceberg as the storage, right? So in the diagram like this, we support Apache Iceberg, we support Delta, we support Apache Hudi, right? Supports all of the popular table and file formats. It can be used as a newer generation of query engine for the Lakehouse, for those like low latency, high concurrency data warehouse like scenarios, right? It has an MPPU architecture, scalable, focus on low latency, right? Written in C++, SIMD optimized, right? It has a caching framework, that's built for cloud storage, for your data lake, to have that data warehouse-like performance on the data lakehouse. Okay, so that's a quick rundown of StarRocks. I forgot to mention in the beginning, if you have questions, please post them in the Q&A. Oh, I already see questions in the Q&A. Submit your questions. We're going to try our best to get to every single question at the end of the webinar. Okay, so now let's talk about 4.0. So performance. So that's to you, Rob.
Sure. Yeah. Thanks for that overview, Sita. Yeah. Let's talk about performance. So performance has kind of always been in our DNA, right? But this year we kind of took it to the next level. Starting from 4.0, StarRocks is 1.6 times faster than 3.3 year over year. And the TPC-DS benchmark is something we've tested on before, and we continue to test on it. Why? Why do we continue to test on it? Well, it's a great benchmark for real-world querying scenarios, specifically in the context of an enterprise situation. But of course, these changes didn't really come overnight, right? I mean, we've made some core operator improvements that really got under the hood to attribute to this performance boost. What are some of these core operator improvements? So the first one being that a lot of our join operations got significantly faster. So things like hash joins, merge joins are able to handle better complex multi-table queries, less memory overhead, better parallelization without any manual intervention from a user at the query level. We also made it so that our aggregations are now using less CPU. So the aggregate operators we're all really familiar with, like count, distinct, group by, are now using more optimized global dictionaries, more optimized hash tables. And third, which I would argue is one of the most important, is we're more responsible at spill handling now to the disk. So in the situation where your queries exceed memory limits, maybe you get out of memory errors, you're going to be getting much less of that because the new partition-wise spill mechanisms minimize a lot of the I/O using and help make your queries perform reliably as your memory needs increase. So now I want to talk about, I spoke about the performance. We've had a great performance increase year over year. I want to talk a little bit about JSON now, going on to our next feature. So historically, JSON has been treated, when there aren't any optimizations, kind of like a black box. You have to parse the full JSON object row by row. Even if you just want a couple fields from it, you end up parsing the whole thing. And using the bottom query as an example, let's say I want something like user ID, region, event timestamp. I may just want a few things from my JSON object, but in reality, say I have on the right-hand side, say that object actually has 1 million plus fields with key value pairs. A lot of traditional unoptimized database systems are going to have to scan that whole object regardless. So the result of that is that there's no indices, there's poor compression, and you get a lot of overhead when you're manipulating JSON objects. Causes your CPU to skyrocket and your I/O to skyrocket as well. Now, there was a time where our JSON support wasn't as advanced, but we've come a fairly long way since then. So I just want to go over maybe the evolution of how we've supported JSON over time. So prior to 2.3, JSON wasn't really natively supported. We had JSON string support. So what were some advantages? Well, we had some basic JSON support. From 2.3, we were able to serialize our JSON objects and add a bunch of functions to manipulate with it. So, converting strings to JSON, JSONs to strings with a JSON type built in. That was our big advantage then. In 3.3, we introduced flat JSON columnar storage, and that allowed for auto columnarization of some of the hot fields. So now, that meant that, we're able to pick apart some of the fields that a user is querying for, and we're approaching something that's more columnar native. Now with 4.0, we're introducing the flat JSON v2 engine, and we get a whole bunch of advantages with that. Like I'll talk about briefly in a second, like indexing, dictionary encoding, and lazy materialization. That takes the flat JSON engine to new heights. And like I mentioned, there was a time where we didn't have as advanced JSON support, but we've come a long way since then. Let's take a look at how far we've actually come in terms of benchmarks. So, looking at our newest benchmark, I would say we have more or less next generation JSON support now, where we're almost 3 to 15 times faster than 3.5. Now we're getting closer and closer to performance that's akin to native columnar storage. So you don't need any flattening. There's no pipeline changes required, and we don't need to go through this hassle of scanning a lot of our full JSON objects. So now you can kind of treat your JSON objects like semi-structured files. That's kind of the result of this. So looking at the benchmark on the right-hand side, we can see this is the JSON bench that we're comparing against some of the queries in the actual JSON benchmark that we used. So I want to actually, now we kind of discussed the benchmark and how far we've come in performance. I want to talk about some of the granular file level structure that we use that actually lends to better JSON support. So going on to this page, I want to talk about how we actually work at the smallest file level. So the smallest file level that we use in StarRocks is a segment, and this segment itself is columnar-based and uses pages. And each of these pages basically correspond to a specific column. And when we have these specific columns corresponding to pages, we're able to actually leverage indices out of the box, because this is how our data is treated for non-JSON use cases. So what do we actually get once we leverage the smallest file unit being a segment? Well, we have this JSON column writer class that sits in between the JSON object and the segment. And that allows us to partition it over and create these columnar page mappings. So with V2, now we get to columnarize more hot fields. We get type inference. So things like your strings, we don't always have to cast or use strings to convert JSON objects to something that StarRocks understands. We can use things like ints, doubles. We can have redundant column inclusion. So if we have multiple columns that have low cardinality, we can combine some of these fields together, so we save space. And as I mentioned, we can save space and treat our JSON object kind of like a semi-structured table at this point. So let's actually talk about some of these specific features now that I've kind of given an overview of how we're actually leveraging JSON to be more columnar-based. What are those features a little bit more in depth? So the first one is dictionary encoding, now, or otherwise known as auto dictionary encoding. What this does is, say we have a lower cardinality field that we're querying, we can basically at query time translate that condition to a dictionary that we have behind the scenes. So say, for example, here on the right side, I'm querying where the region is US, and I may only have, in reality, I may only have, say, a select amount of countries or regions that I'm using. I don't know, say like 100, which is a relatively low cardinality field. So behind the scenes, at execution time, I can rewrite the condition of US to use a dictionary. So it says, okay, it sees like, okay, you're using US. I already have a dictionary that has US in it. Let's retrieve it. And beyond that, I can actually use statistics with the dictionary on each of the pages. So remember, we spoke about pages being attached to a segment. Now I can actually use what, instead of saying, in this page, I have US, France, or Japan, I can look at my min and my max with additional statistics collection. So min would be, okay, I know I have US here. Max being 3, okay, I know I have Japan in here. So with that, I'm able to skip unnecessary data, and I'm also able to reduce I/O and memory usage. Next feature, so ZoneMap and SortKey indexing. So kind of the whole point of this is to avoid full table scans and have closer statistics collection on each page. Now with ZoneMap, we're able to, the main source of performance improvement is it reduces the amount of scanning. So by being able to leverage the selectivity of certain predicates, say like, I want to select by US and in between these set of dates, I can actually sort my pages so that I have min and maxes on each of those pages. And when I have min and max for each of these pages in the segments, I can skip even more irrelevant data. So it's a very big boon in high predicate selectivity. And combining ZoneMap and SortKey, we're able to kind of skip and reduce the full table scans that we had before. So that's kind of a little bit of what ZoneMap is combined with the dictionary encoding that I discussed before. And then late materialization. So what is late materialization? Well, in most traditional execution paths, a database will often, kind of decode the whole JSON object, in an unoptimized environment, decode the whole thing and then filter it. But by the time we get to the filtering, we've already wasted a lot of we've already wasted a lot of I/O on decoding the whole thing. So basically, we're decoding irrelevant dead records or dead fields that weren't even going to be used. So with late materialization 4.0, we've now been able to use kind of like a lightweight StarRocks representation that has filters first. So for example, here on the right-hand side, in the region equals US scenario, StarRocks could read the region field, filter it, and then record the row number in this lightweight StarRocks representation. And then it could read the user ID field according to the required row number that it just collected. So, you don't need to waste CPU and memory on dead records that you wouldn't have used anyways. So those are some examples of how we've additionally helped you save memory and I/O. So let's talk a little bit about data lakes now. Sita, if you want to take over on this.
Yep, of course. In version 4.0, we strengthen our data lake support, right? We always want to provide the best kind of performance to you guys, but on not only on proprietary storage, but on open storage too, right? So let's now take a look at some of the enhancement we did with 4.0, right? First is Apache Iceberg ingestion maintenance, right? So this is a lot of fun. So I remember around a year and a half ago, right? There is one of the StarRocks user that came to me that said, you said your query engine is like 6 times faster, right? 8 times faster, but in production it's the same with the Java-based query engine he was using. After some investigation, it was not an engine issue; it was a data layout issue, right? So slow scans on millions of megabyte Parquet files, just horrible for data scanning, right? And the latency is it's the sum of all of the query planning, the query execution, and the query scanning, right? If you scan really slow, it's just nothing we can do, right? So here we're trying to solve that problem, right? So the small file problem, small file decimates Apache Iceberg query performance, right? And why is it particularly difficult for Apache Iceberg? It's because user often need another tool, to fix their data layout, right? Their Apache Spark, maintenance service, if their company has that, or they're using a kind of like a managed solution, right? Either way, it's very difficult for them to tune, right? To have that compaction like fast enough, right? And also, why do we only hear like a lot of Apache Iceberg users complain about this? Because a lot of users, Apache Iceberg users, are moving their latency sensitive workloads to Apache Iceberg instead of keeping that in the data warehouse. That is a good trend, but we need to keep the data governed as well, right? We need to have bigger files, query ready files, for those kind of use cases. So the goal for StarRocks in this one is to take over the ingestion pipeline as well, and to generate query ready files right after ingest, bigger files, sorted files, right? And also continuous maintenance, right? So on demand compaction, to keep those files healthy, like over, when there's like more ingest come in, right? So keep it maintained, right? And so one tool with StarRocks, query and maintenance to take care of most of your lightweight ETL kind of workloads on Apache Iceberg maintenance workloads, right? So here's what we did, right? So here are some of the say optimizations we did for ingest, right? So first is partition shuffle. Basically what it means is that if you have a lot of partitions and you have a lot of backend StarRocks compute nodes working on that same partition, right? You're gonna generate a lot of tasks. So basically, the number of tasks per Iceberg ingest commit can be the number of partition you have times the number of backends you have. That's a lot of tasks, and for one Iceberg write, right? And now we're able to shuffle partitions to appropriate compute nodes. So ideally, for one partition, only one or a few compute nodes work on that partition, right? So there's less overall number of files, so generating much bigger and closer to target file sizes, right? When writing to Apache Iceberg, right? So and also, we supported local sorting within files. So basically, within the Parquet file, we're able to sort all of the pages, right? So when you do a query, within the file is log in, right? Basically, the complexity after this optimization, if you do sorting, is the log of the number of pages you have plus O of n equals to the number of Parquet files you have, right? So that's really great for performance. Sorting with sorting and partition shuffle with StarRocks Iceberg ingest. And here are some of the performance numbers, right? It really work like a charm, when there's a lot of partitions, right? So version 4.3.4, we already supported Iceberg write, but without this optimization, it's a lot of partition, it just doesn't work, right? And with 4.0, with this, it's no OM issue, right? And the number of file drops dramatically because we are able to combine, a lot of the partitions together. Right. Okay, so this is some benchmark numbers. And also, to be able to achieve that kind of file size, we reuse some of the logic from the query side, the spill operator for our write as well, right? So before in 3.4, we had that problem, uh, our computer is going to OM, right? So it has to be forced to flush out the Parquet files early, right? So generating a lot of small files. And now we have that spill operator. We can hold it for as long as it need until it hits a target file size, and then we do a flush, right? And then this spill is the same spill mechanism we use on the query side. So that's not only a local disk spill, this is also a local disk spill and a object storage spill. So it doesn't matter like how big your target file size is, it's never going to OM because of this. Okay, and on top of that, we introduce a compaction API, right? You can do it in SQL and it's synchronous. And one differentiation of this compaction API is that you can dictate how much resource it uses, right? If you want to like fix a table really quickly, you can basically allocate all of the cores you can, right, to go all in that one compaction. If you want to do it, you can control the resource that you use, to a compaction to fix them on demand, right? Okay, so that's data lake, and then is security and access control. So back to you, Ron.
Yeah, sure. Thanks for handing it back over. So yeah, let's talk about how we've kind of made some leaps within security and access control, particularly in the REST catalog and REST governance. So looking at this, okay, there we go. So REST catalog security. Let's just talk about in general what some of the traditional limits are. So in the past, what we've seen is that a user will log into the query engine. They'll probably call, their identity provider, whatever it may be, maybe Okta, maybe Ping ID, could be anything that they have. You check the permissions using some sort of external permission system. And after that, you gain access to the catalog and storage after the permissions have been granted and checked from the permission system. And then you gain access. But the thing is, in this case, you actually gain access. The user is not really a real person. It's more of a super user that's delegated when you're accessing the query engine. Doesn't matter whether 100 people are using the query engine or a few people are using the query engine. It's usually just one service account that gets granted kind of godlike credentials. And obviously, the issues with this are privilege exposure. The engine has to hold the super user account. You have to have a lot of trust with your engine. And there's long-lived storage credentials that sit inside of the query engine, which in and of itself is a huge risk, because if anybody gets access to the query engine, it basically they get access to your whole lake, to all of your data as well. And then, of course, you get fragmented auditing too, where the situation where you don't know who's accessing what table because there's just one godlike credential accessing everything. So what are the ideal tenets that we would like to live by? Well, we in 4.0, we tried to achieve catalog layer governance and security. So what that meant was consistent authorization across engines. So the single authority is the catalog in this case. It's not the query engine. That could change depending on who your user is. And second is secure and simplified storage, so that your catalog remains as the one authority, and you don't have to keep giving super user access to everybody in your organization. So let's talk about this, from an actual example with a couple diagrams. So how does the catalog enforce permissions? How does that actually work? So the whole idea is that we're leveraging JOT token session integration here. So if I'm, say, Bob or Jane, and I'm using StarRocks, I would have a JOT token file on my machine signed by whatever external identity provider that I'm using. In StarRocks, we're able to integrate external identity providers using security integrations. That's available on our documentation. And once I've received a signed JOT token session or a JOT token file that I have on my machine, I can contact the REST catalog provider. And then that REST catalog provider can go to my external permissions, say like an Apache Ranger, go back to my REST catalog provider, say, okay, everything looks good, and give me temporary vended credentials rather than long-lived storage credentials that we previously had in the super user example. And then once I get the temporary vended credentials, then I can access my object storage just fine. Then it's all hunky-dory, everything's fine. But in this case, the key distinction here is this JOT token session integration, because now we're assigning a token to every single individual user, and that's being hooked up to our external identity provider. There's lots of information about this online in terms of the specs of what goes into the REST catalog, the REST security protocol. But this would be ideally a form of delegation. That's what we're trying to achieve. So moving on from security and storage, let's talk about or security and authorization. Let's talk a little bit about storage and some of the quality of life improvements that we've added to StarRocks in 4.0. So the first one being real-time analytics on S3. So we've gotten to a point where we're able to make this more fast, more stable, more cost-efficient. Traditionally, a lot of writing workloads result into all of these tiny fragmented files, and API costs go through the roof. So we've kind of eliminated a lot of this by a few different features in 4.0. First one being file bundling. Now, in file bundling, we're able to pack a lot of the smaller writes into larger objects to reduce the object count and eliminate a lot of the write amplification that you'll see when you're talking to S3. Second being metadata caching. In metadata caching, instead of having to talk to your object store every single time for every single API call, we're prioritizing serving the metadata straight from the local compute node memory whenever possible to save that call and the round trip time, and really ideally not have any if we already have some of the data stored locally. Third one being smarter compaction. So in 4.0, we've kind of strived to keep data more organized for queries without over-consuming a lot of resources. That kind of helps maintain fresher query latency, and a lot of your queries are able to run faster that way with compaction built in. Some other features to kind of take us to newer heights or newer dimensions of performance, which we previously didn't have. First one being high precision decimal 256. So 256, it's a decimal type for really accurate arithmetic. If you're in a financial services use case or in an accounting situation, you're going to be ideally you'd want to use decimal 256. Notoriously, float or double formats can sometimes be inaccurate. So, for example, on the right-hand side, you'll see here, the example I put here is, add 0.01 10,000 times, or 10,000 times 0.01. And in a traditional data type, say you're using a float, you would expect the left, which is, okay, I get 1,000. But in reality, there's small mistakes that accrue on each addition that can result in some remainder at the end if we're not using super accurate data types to do some of this computation. So given that's the case, we based on demand based of what the users were asking, we ventured toward decimal 256. Now we're able to handle a lot of those larger or smaller numerical value additions, subtractions, products, and achieve what we would expect in this case, which would be the 1,000 result. And that prevents a lot of rounding errors in analytical workloads, in financial services situations. Maybe you're calculating interest payments, PMI, whatever it is. In this case, some other examples that I've listed here, currency settlement, trade reconciliation, modeling, lots of different scenarios. But we're striving to achieve success in other workloads and other data types beyond traditional ones that you may see in a warehouse setting. So we're catering to all different industry verticals here and use cases. The next feature was extended support for multi-transaction or multi-statement transaction. So modern pipelines, data pipelines, they kind of rarely work with single tables. So a single ETL flow could easily have you loading records into a primary key table, updating some dimension table with new attributes, inserting other records and some other fact table, a whole bunch of stuff, and then maybe you're aggregating all of it in some sort of roll up. When these operations aren't treated as a single atomic unit, failure kind of at any step of the way leaves your whole data in an inconsistent state. You could have 100 different insert statements, but if a few of them don't insert and somebody has queried your data in that split second, you're going to get an inconsistent view of what your data is. So it's not just a technical inconvenience. Inconsistent data leads to inaccurate business just being done overall. So in 4.0, we've extended our multi-statement transaction support. So we're trying to strive for the atomicity, the transaction boundaries, the cross-table consistency and rollback that you'd expect in an OLAP database. So starting with the first feature, now we can extend to multiple inserts per table. So inserting, say, for example, on the right-hand side, we're inserting this fact table. You see 3 insert statements. That's completely fine now. We're not limited to a single one anymore. We've extended a lot of our DML support as well, so we can combine inserts and deletes within one atomic transaction. We have streamload support. I didn't include that here, but basically, if we're using native streamload in StarRocks, we can kind of have the same begin and commit blocks, just like we would see with these DML operations on the screen. And then lastly, which I would say is one of the most important, is we have automatic and explicit rollback protection. So we have things like, say you want to insert something, update it, and you're updating something, say the product ID doesn't exist or some object that you're trying to reference doesn't exist. In this case, it would automatically roll back and save you the headache of having to individually roll back all the component statements of that whole transaction. Likewise, you could also use explicit syntax with begin and rollback, so you get that flexibility as well. So that is kind of the whole idea with extended multi-transaction support. Next feature, as of join support. So kind of continuing along the trend of financial services, accounting, high volume data use cases, especially with time series, we're adding as of join support in 4.0. Now, using this as an example, for those who don't know what as of joins are, as of joins allow you to actually get they're great for joining time-based data and sequence ID based data that you might see in finance. So using this example here, if you look at it, after I discuss it, you'll see, okay, you could have used a traditional Windows statement here, but let's walk through the example. So say I have this ticker VOD and I have BT. So VOD and BT, the time that I executed these trades on the left-hand side was at 12:02 and 12:04. Now, on the market, before a trade happens, there's quotes that go out. Say, I'm selling it for this amount. This is what I'm asking for this product, or this is what I'm selling for the product. Those are basically quotes. You have, quotes on the buy side. You have quotes on the sell side. So let's say those transactions happen at 12:02, 12:04. I want the last quote before that trade happened. So in the case of VOD, we can see that the last quote was actually 12:02, and we kind of sliced that little bid and ask out 79.65 and 96.28 respectively, but we ignored the quote from 12:03 because that wasn't relevant to us. So it allows you to get the nearest timestamp relative to another timestamp very, very accurately. Same goes for the BT example at 12:04. Otherwise, if we did have as-of joins, you'd probably have to do a lot of manual work with, say, window joins. You may have to create a temporary table to calculate some of this stuff and aggregate it. With as-of joins, you can do this on the fly. And on the right-hand side, we kind of get the result. Hey, this is the last bid and ask that happened with your trade and quote. Some other features that we've added, so some bells and whistles, more for like quality of life for ease of use. First one is node blacklisting. So you can automatically isolate a lot of the compute nodes that may be unstable. Let's say there's a lot of queries surging through one of them for some reason, maybe based on your resource group setting or your warehouse setting. You can avoid using some of these and isolate them out with some commands. So the scheduler avoids using these compute nodes. Of course, even though they're stateless, there may be situations where you may want to isolate these compute nodes out anyways. Second quality of life feature that we added is case-insensitive identifiers. So say you want to name a database, table, or view with different cases. So this is the perfect example. So instead of orders, let's say I want to use orders with a capital O instead of a lowercase. I can do that, and the database will treat those things agnostically. It'll treat them the same. This is just so, we heard some people having some issues with migrations, toolchain mismatches, and they were saying, hey, can we have the ability to treat these names we're creating in an insensitive manner? And then the last quality of life improvement that we've added is a cluster-wide ID per session for better debugging. So we also got this requested a lot as well. People were going through logs and not able to debug their commands in the front end or back end based on individual sessions. So now there's a cluster-wide ID. Every single session or everything, every single session that logs on for better debugging purposes. So this should make the whole process much smoother when you're scrolling through hundreds and hundreds of lines of commands. So with that, I think that kind of closes off some of the features, some of the performance improvements, security, authorization, quality of life. Let's move on to the roadmap a little bit. Sita, I'll let you take it from here.
Okay, thank you, Ron. And now let's go beyond 4.0 and see what's going to happen, with future 4.x releases, right? So first, real-time intention on the Lakehouse, and we want to provide this kind of real-time, low latency type of thing on an open format, on an open architecture, right, to support not only your BI tools, also your AI agents going down the road, right? So it's real-time analytics, right? So we will keep strengthening, right, our table creation process, right? So we want to build automated table creation, right? So there is no more manual tuning, when you try to create a table, right? So no surprise slow queries caused by data skews or, right, data layout issues. And, so you always have fresh data, and you always have that not only fast, but consistent and predictable query performance, right? And also fast for the Lakehouse, right? We also want to, keep strengthening our support for the open Lakehouse architecture like Apache Iceberg, right? So on the query planning side, we will strengthen our support for those more data lakey kind of queries, right? So bigger queries on massive amounts of data, right? Probably longer latency type interactive ad hoc like queries, right? And also, embrace ecosystem compatibility while bringing our understanding of governance of table maintenance to open table formats, right? So using StarRocks to keep your Apache Iceberg tables healthy, right? This is something we really want to do. I think that's the last step, the necessary step of having that, consistent performance on Apache Iceberg, right? And also we're going to introduce incremental materialized views, right? So incremental asynchronous materialized views, right? So balance between performance and data freshness, right? So now the materialized view, asynchronous materialized view, is you refresh by partition, right? But once you have, incremental materialized view, right, streaming materialized view, you can support StarOS able to support much better data freshness, with materialized views. So actually use materialized views in a real time kind of setting, right? And also with AI, we're gonna strengthen our integration there too, right? So AI powered optimizations and guidance, for table creation process, to how to use materialized view, how to tune the database, right? To use LLM and with MCP, to have that kind of automation, right? And StarRocks MCP integration, right? Continuously improve that, to support all sorts of different kind of workload, for example, like table optimization, right? And actively collaborating with other communities that builds this kind of, SQL BI agents, right? To, they're building tools, to enrich the context, for LLMs, right? For your database, right? So I think in the future, data engineers are not going to deliver static tables anymore, for their stakeholders. It's going to be agents with a context for that specific kind of use case, right? So we're actively collaborating with other open source communities, to bring this whole like agentic SQL experience to all of you guys. And also to expand into more workloads, for example, vector database, to use StarRocks to as a memory for LLM systems, or to use StarRocks to search with semantics, right, with context, right, to use StarRocks as a vector database. So StarRocks already has a vector index implementation with ANN support, approximate nearest neighborhood support, with all of the indexes there, right? And we're going to use in the 4.x releases in the future, we're going to strengthen this support, make it more robust, and also to make the performance even better, right? And also hybrid search enhancements with other types of search, together, right? And also, bigger columns, right? A column that's stored much longer um, um, vectors, right? So bigger column LOB support and performance optimizations. So that's on the workload level. And we're always trying to be open. We want to be even more open, right? And in the 4.x release, we are going to open source StarOS, which is our implementation for the StarOS storage and compute separation design. Right now, it's free to use. You can use a binary, but we're going to open source this around end of year, early next year. And also with multi-warehouse. So this is a feature that allows you to group your compute nodes into physically isolated compute warehouses, to do workload separation, right? So hard, a physical workload separation. You can do compute separation, right? So different type of query workloads, or you can do compute iceberg maintenance separation, right? Or compute ingestion separation, right? So, you can isolate different kinds of workloads, to make sure that all of your tenants, all of your workloads has the appropriate amount of resources to hit their SLA goals at all time. Okay, so this is, we want to be more open. StarOS and multi-warehouse. This is actually all we have. Let's go and take a look at the questions. Okay, I just made public all of the questions. Let's take a look at the chat first. Okay, let's get it. Let me read through the chat. Compaction for which table type? The compaction thing I talked about with Data Lake, that's for Apache Iceberg. Asynchronous Apache Iceberg Compaction API. Let me see if there's any other in the chat. Do you have plans for supporting other Iceberg maintenance job besides compaction? Yes. Now we are able to just compact the data files, right? That's step one, and data files and delete files. And in the near term, we're going to support compacting metadata too, right? So metadata rewrite, right? Rewrite the manifest. Manifests are incredibly expensive to read. Like for one StarOS core to read an 8 MB a manifest file is like it's like a second. So yeah, so we definitely want to do that in the future, and also we want to support near real-time ingest, right? To directly read from a Kafka topic, and to do that kind of near real-time ingest and streaming ETL. That's more like longer term 4.x kind of a roadmap. Okay, let's take a look at. Okay, thank you. Yeah, yeah, we're it's not in 4.0 yet. So for 4.0 for Iceberg, like maintenance kind of thing, is just a start. We're gonna keep working on this because I believe this is the problem we have to solve if we want to get that kind of performance. Thank you. And more questions. Okay, let's go. 14 questions now. If you have questions, please post them. We're gonna try to get to all of the questions today. Are there any notable breaking changes to be aware of when moving from 3.x to 4? Okay, so there are some behavioral changes in terms of some of the APIs. So in the release note, there is a behavioral change a section, right? You can go through that and see if any of the functions you use are changed. Take a look at that. I can share the link. Think here. Let me find it real quick. Behavior changes. Okay. Yeah, I just posted it in the chat. Oh wait, I didn't. Okay, sorry. Okay, so here are all of the behavioral changes for 4.0. Take a look if you're affected by any of them. Do you have plans to add integration with DuckLake? I don't think in the near term we have any plans to support DuckLake, but this is still under like discussion. I'm interested in detailed comparison of StarOS 4.0 versus Apache Doris 4.0, and if possibly versus VeloDB latest version, features, price, performance, etc. Thank you. So we don't really have any like more detailed comparison now, but there is a blog that I wrote comparing StarRocks to Apache Doris. I think the two projects are going in a little different directions, right? I think Apache Doris is more like going toward that search kind of Elasticsearch type of workload, and for us, we're staying in that analytical Lakehouse real-time analysis kind of space, right? You can read that blog, you're interested, but we don't really have any more detailed comparison now. If you understand correctly, queries on 4.0 does not have auto memory error, even they're not efficient. Okay, so by design, so we have a spill we have a spill mechanism, right? And spilling has like different kinds of modes into it, right? You have the auto mode, you have a force spill, so basically spill every single operator by operator. There's still chances that it's gonna OM, but by design it shouldn't if you use force spill. But they're always like edge cases. Our spill just that one operator we didn't support. That one operation we didn't support is still possible, but it should be pretty reliable now with 4.0. So via StarOS 4.0, we can write optimal size files in Iceberg, and also can we run compaction from StarRocks via alter command? Is there any optimizations while reading small Iceberg files? If you via StarRocks form, we can write optimal size file in Iceberg, and also we can run compaction. Yes. So we can do a compaction. Compaction is synchronous, so you can control the amount of resources that it needs, that how fast you want to run it, right? Optimal size files. Other reading small files. there's really not much we can do. Besides, if the size is very, very small, there's really not much we can do. We can cache it, but the first query is gonna suffer. So not really any specific optimization for small files. Next question. How does this work in case of querying from streaming platform like Kafka? And how is it better than Apache Pinot? Streaming Kafka. Okay. Yeah, Pinot is like Java based. SIMDs is really important. Right? It's with OLAP, it's always like the amount of it's always just the more batch you go, right? The more data point you can process in one single operation, the more you can do that, the faster it goes, right? So that's why we use columnar storage. That's why we do vectorization, right? That's why we do SIMD, right? So we want like multiple data points in like one CPU cycle, right? So that's like mainly the performance difference. It's a big performance difference between StarOS and Apache Pinot.
And if I could add to that, Sita, too,
Yeah,
like
yeah.
there, we have like we allow you to use different ways to query Kafka out of the box. So we have like routine load, but we also integrate with Kafka Connect, depending on your ecosystem. And I would say like just extending it further, some of the stuff we talked about just in general with external catalog support. Apache Pinot is a little bit weaker in external catalog support unless you go to the managed enterprise version. So just a couple additional things to add on there that may help you in your research.
Okay, next question. JSON improvements only for shared nothing architecture or both? Wrong?
Yeah, so the improvements should be across the board. They're in shared data and in shared nothing. We wouldn't implement the feature just for shared nothing. A lot of those benefits don't get put to use unless they're across the board. So it's also in shared data as well.
Makes sense. Thank you. Next question. Can you do multi-statement transaction with submit task? I think we only do like a begin and end, right?
Yeah, it's just
Yeah.
so it's begin and commit. That's like what and then we support begin, commit, and then roll back.
Yeah.
There's no submit yet for that. Hopefully in the future. We've been the whole multi-statement transaction thing started in 3.5 as like kind of like a beta feature. 4.0 we're trying to like lock down and expand it to all of the different syntax that we have. But hopefully in the future. As of now, I don't believe so.
Yeah. Thank you. As the spill performance for regular expression operator for Iceberg tables improved. On 3.4 and 3.5, there were memory issues in CN. For this, I don't think we have any specific optimizations for regular expression, but we do have like across the board, memory optimizations. For example, like metadata in FE, metadata cache in FE, we did a lot of optimizations there, and also with a lot of the operators, just general memory, optimizations, but not specifically for regular expression. But if you have an issue, if you can create a ticket issue on GitHub, we can take a look and see if there's anything we can do. Okay. Have there been any improvements in monitoring, real-time tracking in the UI?
Yeah,
Ron,
actually, I do believe there is an improvement. If I remember reading correctly in the release notes, there's a display of running and pending statuses for some queries that are in flight. At the process level, I think that's what has been enhanced. I'd be curious to know, what you've been using now. Feel free to share that too. Of course, we have, out of the box support with like Grafana and Prometheus as well as we have a pre-made JSON dashboard for that you can use. But in 4.0, if you look at the release notes, there should be something to do with in-flight queries that you can track and look at the status. So that is, I think, the biggest thing.
Thank you. Next question. We already have had case insensitivity. No? Maybe we got backported to some other versions. Which version are you on? Um, that I'm not sure. Wrong?
Yeah, I don't believe we had it before.
Yeah.
It's possible it could be another
Yeah,
version
probably
though.
like backported to one of the 3.5 or 3.4 versions.
Yeah.
Yeah, but if with your, I would love to learn about your like which version you're on. Next question. It looks like optimizations and features are being created for Lakehouse implementation of StarRocks to improve real-time performance with everything that has been added. How does performance compare to the share nothing architecture? So, yeah, so there are three things, right? Share nothing, share data, that's our own table format, and also the Iceberg format, right? We've been working hard to close the gap between, like having an object storage versus like scanning directly from our internal, like your SSD, right? That's caching, right? We've built a lot of things, to make sure that hot data is not evicted, right? We have segmented caching, right? It's a RU implementation, right? And we keep enhance that, to make sure that the difference there is not that much. And also like between the Iceberg and our table format, we're porting a lot of the feature to Iceberg, right? For example, we have um low cardinality dictionary for our own storage, right? And we even ported that to to Apache Iceberg. So basically, to create those dictionaries on the fly and then utilize that for query. So we're still in the process of doing everything, but according to the TPC-DS benchmark test, the difference between share nothing and share data is almost minimal, nothing. And between them two compared to Iceberg is less than 10% difference on TPC-CDS 1 TB. So wrong. Anything to add there?
No, yeah, I think you summarized it pretty well.
Okay, great. Are incremental materialized views intended to replace, enhance, or live alongside of the existing partition materialized view feature? This I think ultimately it should replace because it's just a better feature once it's fully built, right? But a lot of the incremental thing, you have to manage state, right? So we need to like implement them kind of one by one, operator by operator, right? So I think they're gonna coexist for the near future, and then ultimately you should replace the partition based asynchronous materialized view. You share the compaction API. Does it work for Athena-Iceberg table as well? Athena-Iceberg table, is that the S3 table? If it's like REST compatible, it works. Right? If it follows the Iceberg spec and the catalog, StarRocks can read from REST catalog spec. If it follows that, we're able to compact. Doesn't matter what Iceberg it is, as long as it's standard, right?
Yeah, I'd be maybe if you want to like clarify what you mean by Athena-Iceberg, I think that would help. Because I mean, Athena, you can read, you can do time travel, you can kind of do all the queries on it. But I don't know, like Sita said, maybe you're talking about S3 tables. Is just better clarification would be good, I think.
Yeah. Yeah, I'm not that familiar with if they have a Athena Iceberg table. Yeah, but there is a like a managed version of Iceberg. That's
Yeah,
a S3 table. Not sure if you're referring to that, but
yeah.
oh, three more questions. Okay, let's keep going. I have a meetup in like 7 hours, so if we don't run until that, we're fine. If I have questions, ask. Right. If we're not able to get the answer to today, we're gonna have a blog post that cover all of the questions. How querying JSON are optimized in case of shared architecture. Slides what I saw that while writing to local storage, it organizes segment files beforehand, so it could be queried optimally. But what about regular case objects, store and writing data in Parquet?
Okay, yeah. So, I mean, so yeah. You saw what the diagram was in local storage, but behind the scenes, whether you're whether you're using shared nothing or shared data, we're still leveraging segment files to do the querying. So, in the case of writing to parquets, you'd be leveraging the features that we use already in shared data. So the segment files aren't exclusive to shared nothing. Like the JSON writer class that sits as an intermediary between the pages and the segments and the data that you're querying stays consistent across both.
Yeah. And also like writing data in Parquet, we this is really for like StarRocks internal format, so share nothing and share data. So in Parquet file, that's more of like data lake, right? So this is not for like Parquet files, I believe. I may have missed it, but how often does the compaction API run? Do we set it on a cron schedule or something? Yeah. So it is a API, so it's not managed yet. We are going to make it managed in the future, longer term. But now it's just an API you run synchronously, right? You run in SQL, you run that, and then it's just a one-time thing, right? If you want to use it on demand, if you want to have a scheduler for that, it's your choice. Next question. Correct. Thank you. Any other question? Thank you. Thank you, everyone. I think that's all of the questions we have today. We're just at the top of the hour. That's great. Thank you, everybody, for joining. And be sure to join StarRocks Slack channel if you haven't already. Thank you so much for coming. And thank you so much, Ron.
Thank you.
It was a lot of fun. This is honestly like my favorite type of webinar to do.
Yeah, it is. Yeah, it was
really
a fun
appreciate
time.
that. Really appreciate that. Thank you.
Thanks for all the questions, guys. All right. Take care.
Appreciate that. Oh, wait, there's another. Oh, more questions.
Oh, one more. Okay.
So you should write Iceberg data via StarRocks to get benefits on query. Write it via Spark won't organize that optimal way, right? No, the JSON thing is not for Iceberg. It's for like internal storage. Can we write Parquet v2 in StarRocks? That honestly, I don't know. I'll figure that out. I'll figure that out. I'll get back to you. Okay. Appreciate that. Thank you, everybody, again for joining. Thank you. See you guys again next time. Thank you.
Thanks. See you guys. Bye.